Hello everyone, and I'm Vinicius, and I will present about our work, a comparative study of phishing activity detection approach in maritime surveillance. The other co-authors are Tiago, Diego, and Sandeep. In this presentation, I will address the following topics: a motivation of this work. In the background, we will talk about some previous approaches. In the vessel trajectories, we will give a brief explanation about the characteristics of the vessel trajectories. I'll talk about some AS data and preprocessing. In the models, I will show the machine learning models that will be utilized in the work. And in the experiment parameters, I will show the parameters used in the models and the experiments, and the results and the conclusion. Maritime authorities have a hard job monitoring the several kinds of activities in the sea, and one of those activities is illegal fishing. Maritime authorities must track fishing vessels to ensure that fishing activities are limited to the permitted areas. If illegal fishing is suspected, resources must to be allocated to intercept and inspect the vessels. A false flag by the Maritime Authority is costly, so it's important to use accurate detection methods. One way to detect illegal fishing is by determining whether a vessel trajectory behaves like a fishing trajectory. Therefore, we need to find in the literature an approach to detect fishing behavior on a vessel trajectory with a high rate of true positives. In the literature, the detection fishing trajectories is addressed by several works using AES sensors data in machine learning models. Models like LSTM, long short-term memory, and the convolutional neural network are most commonly used in the AES raw data. Other works transform AES data into trajectories and then use the trajectories-based data as input in the models. Models like logistic regression, decision tree, support vector machines, random forest, and neural network models can be used in the trajectory-based data. In addition, there is no work in the literature compared this approach regarding accuracy and time performance using the same dataset. Our main objective is find an approach for detecting fishing trajectories with a high accuracy. For this, we will implement the main approach found in the literature, and then compare the accuracy and performance of approaches using the same dataset. We use the global fishing watching dataset combined with a non-fishing vessel dataset. We chose this solution because we want to have a well-distinct kind of trajectory. Sometimes in the vessel, the crew forget to change the status of the AS equipment. Then we have a wrong label in the data. Before talking about some trajectories, I need to talk about what AS is. AS stands for Automatic Identification System. It is equipment installed on the vessel that automatically reports the ship's identity and location. Other receives can receive the signal up to 20 nautical miles away. With regard to vessel trajectories, they are composed of a set of AS messages. AS messages have data such as latitude, longitude, reading, speed, MMSI, where MMSI is Maritime Mobile Service Identity. It's a kind of vessel ID. In the figure on side, we can see examples of vessel trajectories. We can see two kinds of trajectories: sail and fishing. The sail trajectories tend to follow a straight line, while the fishing trajectory tends to have a singular trajectory that's characteristic of a fishing trajectories. It's important to say that fishing vessels take these trajectories only in the fishing spots. When they are just sailing, they behave like normal vessels. From the historical AS dataset, we first need to pre-processing them. So in the figure on side, we can see the dataset distribution. The kinds of vessel with more data is cargo, tanker, tug, and fishing vessels. From the raw AS data, we use the Python GeoPandas library to build the geospatial objects. Then we use the Moving Pandas library to transform the geospatial data into trajectories. From these trajectories, we can apply aggregation functions to calculate averages, standard deviations, and variances. After build the trajectories, we apply some filters. Average speeds less than 1 and average speeds greater than 50 were dropped. It doesn't make sense to use trajectories when the vessel is stopped, and trajectories with speed greater than 50. It's impossible. The other filter was the trajectory must be at least 3 points. For building a trajectory, we need just 2 points, but we need to at least 3 points to calculate the angle of the movement. So in the literature, there are two types of preprocessing approach. Use the raw data and using the trajectory-based data. In the raw data, we have latitude, longitude, speed, course, and timestamp data. And in the trajectory-based data, we have trajectory duration, course variance, speed variance, trajectory length data. After the preprocessing, we have 7,336 trajectories for each class. In the literature, we use the two preprocessing strategies aforementioned. We can find the following machine learning models with the preprocessing strategies. In the raw data, we can find convolutional neural network, long short-term memory models. And in the trajectory-based data, we can find logistic regression, decision tree, random forest, support vector machine, neural network models. Hence, we use these models as comparative. Given the preprocessing strategies and machine learning models that we use, we will now present the parameters of the models used in the experiments. In the logistic regression and decision tree random forest and the SVM models, we use a grid search to find the best parameters like kernel, gamma, degree, and regularization. In the neural network, we use architecture with 4 dense layers of size 32, 16, 8, and 2, and a dropout of 0.2. In the convolutional network, we use a VGG16 architecture. We transform the trajectories into images of 32 by 32 pixels. We use a Bressingham interpolation algorithm to construct the missing pixels in the image. Finally, we insert the speed and direction data into RGB array, where the R was used for the color, and the G for speed, and the B for direction. The number of epochs to train the model was 100. An example of the trajectory image built can be seen here on the right. In the recurrent neural network model, we utilize LSTM layer and dense layers of size 102. A softmax function was used as activation function, and dropout of 0.2 was used. A pad sequences in trajectories with a maximum length of the 500 was used, and a number of epochs equal 100 was used. In the experiments, we divide the dataset into training and testing, where 80% was used for training and 20% for testing. We use a cross-validation techniques where they randomly shuffled the dataset and divide it into k equal 5 parts. Each group was made by preserving the percentage of samples for each class, and each k was utilized as validation in the training. Finally, the best weights of the models were stored to test. To evaluate our results, we use the precision, recall, and F1 score metrics. The precision metric counts how many times the model is correct in comparison to how many times it tried to be correct. The recall metrics compares the number of the correct predictions to the total number of the correct predictions. And the F1 score, on the other hand, is a metric that balances the precision and recall. Here we have the results. We can see that the LSTM was the best model in the all accuracy case with 1.0, and the random forest was the second best precision with 0.87. The precision is the most important metric for our problem, because when the Maritime Authority decides to inspect a vessel, it needs a high degree of reliability. On the contrary case, the resource could be wasted in the case of only error. Regard to execution time, the slowest was the LSTM with 15 seconds, and the fastest was the decision tree with 2 milliseconds. In this case, the LSTM was 1000 times slower than the second best model. This information can be relevant in the case of the IoT scenarios and the thousands of vessels. We have here the training performance. Despite the fact that it was offline training in some areas, the navigation may change, so this training must be redone regularly. Depending on the size of the database to be trained and the available resource, this information may be useful in the future works. Then, in this case, the fastest model was the logistic regression, and the slowest was the LSTM. Now we have some conclusions about the results. The LSTM model has the highest precision and recall with 1.0. The second best model was the random forest with 0.87 precision, and the LSTM required a significant amount of processing time, 1000 times lower than the second best model. The LSTM model has the slowest time to train, 2200 times slower than the random forest model. In the offline scenario, the time is not important, but in an online edge compute scenario, it can matter. The LSTM model showed much better performance than other models because of its capability to deal with time series problems, mainly in the cases when they compare a long trajectory with a short trajectory. Long trajectories tend to have a high variance in the speed and course trajectory, penalizing the strategy to use this data in the models. The same situation can occur in the CNN model when the trajectories are transformed into images. The model will compare a long trajectory in an image with a short trajectory without taking account the trajectory duration and length. The performance of the LSTM architecture may have been enhanced by the use of the latitude and longitude data, which were unavailable in the trajectory-based approach. The fishing spot may have favored the detection of fishing trajectories. because the vessels like cargo ships, tankers, and tugs normally don't visit these spots. In a scenario of IoT deployment, where models may need to process data in real time or near of real time, the time performance of the model can be a critical factor. Thus, in a naval spec situation where severe resources need to be allocated, like Navy ships, crew, environmental inspectors, drones, and others, where a false positive can be expensive, we can conclude that the best solution is the LSTM. Please, for any doubts, you can email me. Thanks for watching.